Good morning, ladies and gentlemen, and welcome to the first Genius webinar, SatSurf and SatSurfer, Understanding a GNSS Received Signal. This is Gabriella Povero speaking from Torino, Italy. I am the head of the Higher Education Unit. Here you go, and you can see me now. I'm involved in the navigation technologies area at the Istituto Superiore Mario Boella in Torino. Let me first briefly introduce my research center for those of you who are not familiar with it. So the ISMB is a non-profit research and innovation center operating in the ICT domain. ISMB was founded 12 years ago, well, at least almost 13 years ago, by a bank foundation, the Compagnia di San Paolo, and Politecnico di Torino. And now we are 150 researchers, more or less, working on 50-year R&D projects. As you can see in the picture, we are organized in research areas, which are the columns, the light blue columns, and I'm involved in the navigation technologies area. Then we have some strategic projects that are the green rows, which impacts on all the research areas. In particular, my research area, which is the navigation technologies one, is focused on advanced technologies for positioning systems and global navigation satellite systems receivers. My area is organized in 3 research units. Mine is higher education, but then we have people working on GNSS platforms for safety and environment and GNSS core algorithms. My research area is, however, not only made up of ISMB team, but we have also some people working at Politecnico di Torino University, which is the oldest technical university in Italy. So we are a joint team working on satellite navigation, and the name of our team is NavSAS. Our team consists of 25 researchers. More of them owns a PhD in electronics engineering. And our focus on top of the GNSS technologies is also the international cooperation. So we promote exchange programs with universities and research institutes. We host PhD students and visiting researchers. From the technical point of view, our focus is on advanced architectures for GNSS receivers, the design of new GNSS algorithms, software radio implementations, Earth observation based on GNSS signals, smart systems for road transport and energy saving, emergency management, safety and liability critical applications, and then, of course, higher education and technology transfer. Today, we can hold this webinar thanks to a project that is funded by the European Commission 7th Framework Program under the supervision of the European GNSS Agency, GSA. And so GENIUS stands for GNSS Education Network for Industries and Universities. Its focus is on building strong links between universities, research institutes, and industry. GENIUS implements measures to strengthen GNSS education and to foster cooperation between education, research, and business. It enables technology transfer through an industry-focused training, internship, and PhD program. So, GENIUS is running now since 1 year, and we have started these webinars. We will have a total of 4 webinars during the project lifespan. Genius will last until the end of 2014, so we will have 2 years more to deliver these webinars. The next webinars will be given by the GAGE group from UPC Barcelona later this year on the GLab tool. And then we will have additional 2 webinars in later 2013, probably the last quarter of 2013 and beginning of 2014. So now let us start with the outline of my webinar today. I will give you a short introduction of the reasons why we start developing this suite, the SatSurf suite. And then I will briefly describe the 2 components of the suite, the SatSurf hardware platform and the SatSurfer software suite. Then we will have some examples on how to set up the SatSurfer and some demo and possible examples of exercises and information that we can get from this suite. And if we will have time, I will shortly describe a possible application that we have developed for coming after the ideas from SatSurf and SatSurf. And then very shortly some hints of the NavKIT, which is an educational tool where you can find also a description of SatSurf and SatSurfer if you are interested. So let's start now with the introduction. And first of all, with the motivation. Why we decided to develop SatSurf and SatSurfer. Well, as a matter of fact, we started from the idea that GNSS technologies are becoming a key element in many wireless applications. Most location-based services and systems are employing standalone GPS or GNSS in general, GPS or GNSS plus augmentations space-based, or assisted GPS or differential GPS as core technologies. And there is a need from academy and companies to train those people that are involved in the development of these applications, such as engineers, technicians, but also students that will become the future engineers. So starting from this, we also find out that often educational and training offers are more theoretical, and so there is a limited space to labs or training on the job. So there is a demand of tools facilitating hands-on sessions so that learners can, let's say, touch with their hands what happens inside the GNSS receiver. So our motto was, as a conclusion, with SatSurf and SatSurfer, engineers, technicians, and students learn how to surf GNSS. So what is the SatSurf? Well, it is a tool consisting of hardware and software components that was specifically designed for R&D and educational purposes. We have the SatSurf, which is an hardware box, including GPS and communication functionalities, while SatSurfer is a software suite running on a standard PC that gets and processes data from SatSurf. So let's have a deeper look at the hardware platform first. So we have this hardware box. You can see it, how it looks like on the left-hand side here, and how it looks like inside. It has a GPS receiver module, and as a matter of fact, it can accommodate different types of GPS receiver. One GSM GPRS module, one standard GSM antenna, you can see it here. One GPS patch antenna, well, the antenna is here, and here is the connection inside the board. And we have a USB input-output port through which we can connect this platform to the PC. It needs, of course, an external DC power supply. A typical 12-volt power supply is fine. And there is the possibility to have an automotive connector for kinematics data log. The GSM module is used to implement assisted GPS services, OMASUP compliant, or to get differential GPS corrections. The hardware architecture, so it's, okay, we come from the USB and USB converter, but then on the board we can distinguish the communication unit where we have the modem, we have a telit quad band, and the GPS unit where we have the multiple GPS socket and a buffer battery with some upgrade connectors for MuBlocks or SURF, and then of course the power supply circuits. As I was mentioning, the SAT-SURF hardware platform may accommodate different GPS receivers, and up to now these 5 are those available. So MuBlocks 5, MuBlocks 4, a GPS module based on SURF star 3, another one based on SURF star 2X, that is the GPS compliant and it's a high sensitivity GPS module, and the SkyTrack Venus 6. As for the GSM module, we have inside the telit quad GSM module, which is a multiple GPRS connection with the CMAC multiplexing. For what concerns the software, so the software, the SAT-Surfer, is a tool that enables the acquisition and processing of data from the SAT-Surf. So we can say that SAT-Surf can talk with different GNSS receivers using their binary and so proprietary protocols. So together with the SAT-Surf, we can say that it represents an announced evaluation kit managing different kinds of GPS receiver and enable a communication interface through the GSM quad-band model. So we have the SAT-Surf getting the data, passing them to the SAT-Surfer, and from the SAT-Surfer we have the graphical user interface that shows us the data, but we can also log this data on the hard disk for post-processing. Looking at the SAT-Surf architecture, we have the SAT-Surf hardware, which is connecting to the core application of SAT-Surf through drivers, of course, drivers for SURF, MuBlocks, and the other receivers, the driver for GSM modem, the driver for N-trip, the GPS, and so on. Then we have the graphical user interface. You can see it here on the left-hand side. And in the graphical user interface, I can set all the parameters and decide which must be the settings for the hardware. So pass them through the core application and then through the hardware. And then, of course, I can log the received data on my storage in different formats, MATLAB, text, Rhinox, KML, and we will see it later, all the possible formats for the data log. So which are the functionalities of the subsurfer? Well, of course, it can display the most important raw data and positioning information in real time. I can also log and export automatically any raw data for post-processing, for example, using MATLAB, and this can be very useful also for training and educational applications, so that students can then post-process and get different graphics and figures and try to understand what's going on. It is possible to test different GPS receivers so that we can compare their performance in different scenarios. It's possible to test assisted GPS functionalities and performance, for example, enabling supply procedure. Or there is the possibility to conduct an analysis of differential GPS techniques, and so test the performance in different conditions. Before going on with the subsurfer setup and demo, let me just send you a very short poll so that we can have it some statistical information from you. And here it is. I'll give you a few minutes to answer. Thank you. Okay, so while you are voting, thank you so much for voting. So we can now, if there's still someone wishing to vote, otherwise we can continue, and I will show you some screenshots from the subsurfer. Okay. And here you are, for your information, the results. So half of you, this is the first webinar. Okay. So here we are, and we can go on with the demo and examples. One moment. And so now we can start with the demo. This is how to register. So you can put the license number here, send an email to get your activation key, include the activation key, and register the program. After the program has been registered, we can now start put some settings for our subsurfer. So here it is. We can choose the receiver type, mu blocks, or the other kind of receiver I can have. my own receiver, for example, I can choose the protocol, UBX or NMIA. The desired link, so through TCP, and in this case I have to put the IP address or COM port or file or GPRS, and also in this case I have the IP address to be included, or the COM port. In this case we will choose the COM port. We can also select the type of DGPS, so standalone, local area, RTK, SBUS. In this case, we will choose the SBUS. And if I choose this SBUS, I can choose the satellite I wanted to use. So in this case, 120. And so now I put the settings. This is the first kind of settings, but I can I have many other settings. So now we will see how to set the wide area DGPS. I can have an external source if I do not use the direct receive, the receiving from the satellite. So, for example, I can select the receiver or no receiver, or the network. In this case, I have the substantial receiver, and I have to select again the TCP, the satellite, and username and password when requested. I can also set the local area differential GPS. We can have simple, in this case correction coming directly from source with any kind of protocol, or with this kind of protocols, or N-trip. And in this case, we again connect to a server which provides the corrections. So we can put username and password and the frequency to update the corrections. Then we can set the data log. So, for example, here we can see all the possible logs and formats. So this is the data that I can select and log, and the types of log: RINEX2, RINEX3, KML for the position, RINEX navigation, and so on. RINEX can be static or kinematics, and in the case of static, in the kinematic mode, I have no settings. If it is in the static mode, I can put the antenna position. For what concerns to the MATLAB log, here there are all the possible logs, and the data can be split according to hours, dimension, size, or I have no split. Then we can go on with our settings and see how to set the GSM. So if I want to use the internal modem, I have to provide the PIN and the access point and select the connection. Again, I have the COM or the other possible solutions, TCP. But in this case, we will select the COM. For what concerns the assisted GPS, I can select the type of assistance, the frequency with which I receive the assistance, the kind of restart if I am interested in measuring the time to first fix in different conditions. And then there are all the information that I can request through the assistance, the almanac, the UTC model, ionospheric model, and so on. The reference location, reference time, and so on. Another parameter, another set of parameters that I can set is the parameters of IMU, and in this case users can choose the kind of IMU. There are some kind here already mapped, the time of calibration of the gyroscope, and so 30, 60, 120, and the type of connection to the IMU. In this case, we have the COM. In addition, I can also set the a local PVT, so I can load a DLL, a driver with a local PVT engine. This engine may contain different algorithms, and I can select one of these algorithms, setting the elevation mask to different values, for example 5, the satellite C/N0, and the period with which the PVT is calculated. And then I can set the source for the observables. So, for example, navigation data from, in this case, we will select GPS, assisted GPS, augmentation from wide area DGPS. Or I can after all these settings have been done, I can, in addition, save the current configuration or load a previously saved configuration. So in this case, we are saving our settings, or I can load previously saved settings. I can set the current configuration as default, or I can load another configuration that was set as a default. So, after I have set all these parameters, what I can finally do is let's connect. And here we are. So we can see the satellites, the positions, the 3D errors in meters with respect to the reference point, the kind of positioning, the different parameters of DOP, the satellites in view, the positioning type, in this case space-based, augmentation systems, the satellites in view, the satellites that have been used for the fix. For each satellite I can see pseudo ranges, Doppler, carrier phase, C/N0, time of the week, week number. Here there are some information about the firmness and its state. And then, so while the SAT surfer is working, I can also have more details on the view data. So for example, I can have wide area connections or the GPS observables. For what concerns to the fast corrections received by wide area connections, here they are. I can also see all the messages given by the receiver while they are arriving, while they are provided by the receiver, and the status of the applications. Then I can also see the estimated position using Google Earth program. And so here we are, and this is our roof. And I can also zoom to see the different fixes that have been done. In addition, finally, there are some commands that I can give to my tool. And in this case, okay, of course I can disconnect. I can have different kind of restart if I'm interested to see the time to first fix. So in this case, for example, hot, and I see here the time to first fix. I can request, send to receiver some asynchronous request. For example, for ephemeris. For local area, I can start and stop the assistance data. For GSM, I can connect, disconnect, or request network parameters that will be included in the log file. For what concerns the assisted GPS, GNSS, I can start and stop or send a request. For what concerns the PVT, again, I can start and stop the local PVT or request it asynchronously to my local PVT engine. I can also have a look at the log directory, and I can also start and stop the IMU or execute a command. So here we are. Now we can have a look at which are, very shortly, which are the parameters that can be logged by the SAT surfer. And so, as I told you, SAT surf allows to obtain from the GPS receiver the available raw measurements and not only the simple NMIA output, and each GPS parameter is logged with a related GPS timestamp, so each parameter can be aligned to the evolution of the others. These are the list of all the parameters that can be logged by SAT surf. I'm not going too much in details. However, for position, of course, the three components of position and the components of velocity, latitude, longitude, altitude, the error with respect to a reference position, the position type, the speed, the amplitude of the velocity vector. For what concerns satellites data, the number of satellites in view, number of satellites in fixed, so the number of satellites that have been used to compute the PVT, the list of the satellites in view and of those used for the fixed. Of course, the time data, so week number, time of the week, GPS time, the leap seconds, the time for fix, and the GDOP, PDOP, the horizontal DOP, and the vertical DOP. Then per each satellite in view, we have some raw GNSS observable. So the satellite identifier, the pseudo-range measurements, the carriers to noise density ratio, the Doppler shift, the ionospheric parameters, and so on. All the raw measurements are saved for all the frequencies supported by the GNSS receiver that is included in the subsurfer. Then we have some EGNOS-related messages, so fast corrections, long-term corrections, integrity satellite information, the covariance matrix, and so on, the wide area degradation factors and the wide area ionospheric corrections. Again, some parameters for differential GPS RTK raw correction messages, so all the messages coming from, for example, the N-trip network. The messages related to the assisted GPS, those for the applied differential corrections, and I have some parameters also related to the custom PVT parameters, so the local PVT algorithm that I may be interested in using. And finally, we have the parameters related to GSM networks and IMU data. All these parameters can be logged in different formats, so normal ASCII text or a MATLAB file, binary, RINEX 2 and 3, in the Microsoft Office Excel format, or in a KML file or NMIA. Pardon. And here are some examples of plots that I can get from the data that I logged with the SatSurf suite. So, for example, in this case, we have a satellite sky plot which represents 4 hours data collection, and where I can show students, for example, the position evolution of multiple GPS satellites in view. Or I can select one satellite, for example, the number 5, and in this case analyze the Doppler frequency evolution for one satellite versus the GPS time. And so, of course, I can see how the Doppler is decreasing while and is changing the profile while the satellite is traveling in the sky. Or, for example, I can make a data collection in different situations and then compare the carrier to noise density ratio measurements for one satellite in different scenarios, for example, outdoor, light indoor, or deep indoor. And here I can see the C over N0 time evolution for one of the satellites. Or I can also compare 3D positioning errors with respect to the coordinates I provided for my antenna in the 3 different scenarios. In this case, again, we have the deep indoor, the red one, the light indoor, the blue one, and the outdoor, that is the green one. And I can also measure the standard deviation of the measured position with respect to the mean position. And I can show to students or ask students to build their own routine to evaluate these parameters. Or I can plot the ionospheric delays evolution for 5 satellites versus the elevation. So these are, of course, only examples of what I can do, but of course we can imagine many others. So in summary, we saw that the SatSurf allows users to log raw GPS and GSM data, may embed different GPS modules. It is equipped with a quad-band GSM GPRS modem for NavCom integration, and allows the storage of raw data in different file formats. So we can say that this is a kit that can be effectively used to test all the receiver features, assisted GPS strategies, and differential GPS techniques. But it can be also an educational tool, since we can develop several exercises with solutions for students. And so it's a perfect tool for a lab, for example, dedicated to ICT technologies. In addition, it's done with the COTS components, so it's ready to use. We are using it in hands-on sessions in classing of our specializing master in navigation-related applications, and usually students really enjoy using this tool. I have just to mention that SatSurfer has been developed by the NavSAS group, as well as the design of the SatSurf, but the SatSurfer is manufactured and distributed by an Italian high-tech small and medium enterprise site, SRL. And here you can find the link to their websites. So just a few minutes to show you an idea we had. This idea came from the fact that here in Torino we are very close to the mountains, to the Alps, and so we are often going just to walk on mountains, and we are in contact, some of us are in contact with the Alpine club, Italian club, and so most of us are aware of need of a low-cost device for precise surveying the mountain footpaths and tracks. And for example, at present in Italy there is not a common strategy to have to create a uniform footpath database. There are some isolated initiatives, but many times the people involved are not technically trained and use mass market device, so the quality of the track, the survey track is not good, and there is no guarantee of the collected data. So we had the idea to develop this tool that is the mapper, which is a prototype, of course, and it comes from the experience we had from SatSurf and SatSurfer. So it has been created with the aim to build a footpath mapping device to take it as much simple as possible so as to guarantee an improved accuracy. We made it a waterproof box containing a microcontroller able to pilot the GPS chipset and to log GNSS raw data on a SD card. And then the idea is to have a server which automatically processes the incoming data using differential techniques. So the server uses as reference the RANX file made available by a local area DGPS infrastructure. For example, here in the Alps we have quite a good coverage. So this improves the quality of the tracks with respect to those recorded in real time by trackers. And this post-processing phase allows us to release a quality certificate assessing the accuracy of the track. So this is the idea. You keep your very simple box, very small box with you while you are walking on the mountains on the track. You can push a start and stop button. You can also push memo if there is something you want to make a note, to record. So you push the memo and you write down somewhere your note, and you will be able, in the post-processing, to put together these two data. When the stop button is pushed, the log is recorded on the SD card that can be then easily inserted in a PC where through the data connection, a web connection, the recorded track can be sent to the server, and you can get the certificate. So this is a possible application that we thought about. And in case you are interested in having a deeper view on GNSS or on this subsurf suite, you can also try to see the NAVKIT. So the NAVKIT, you can log on our website, www.navsas.eu. And here you will find a button. Pushing this button, you will be requested to register. This is just for simple statistical reasons. So we know how many people and from where they are using the NavKit. And you will receive an address, password, and username to log in. And what you will see is this. So we have different chapters. The first unit consists of 7 technical chapters, let's say, with the basics on navigation satellite systems. So these are multimedia short lectures. So there will be a talking head here, and here the slides displayed. But there is also a chapter introducing subsurfers that has an English version and also a Vietnamese version for those of you that are listening us from Vietnam. So this concludes my webinar. Before closing, let me just set another poll. Here it is. So, what is your main interest in subsurf suite? So perhaps you may think to use it for teaching or training purposes, or to prototype a GNSS application, or in this moment you have no specific interest in the suite. And many of you have already voted. You are still voting. Okay, so I think I can close and show you the results. So I may say 1/3, 1/3, and 1/3 for teaching and training, prototype, GNSS application, and no specific interest now in the suite. So I think we can go on with very short closure, just to thank you for being with us today. Our website is www.navsas.eu if you are interested in having additional information on other tools that we have developed and that maybe will be the topic of our next webinars. For example, we have a software receiver called Soprano, or a signal generator in simulator called Infuels, which could be of interest. The website, the general website of my institution, www.ismb.it, or if you wish to contact us, navigation@ismb.it or gabriella.povero@ismb.it. And my very last information is the second Genius webinar from Barcelona, Spain is coming soon, and so stay tuned. Thank you very much.